So in this presentation, what we're going to do is explain to you mainly about what exactly GOAT network is and exactly how we're going to be scaling Bitcoin and exploring ZKM on a layer 2 with GOAT. Okay, so the point of the presentation that I'd like to bring to you, if this, okay, can we go back one slide? Can we go back? Yeah, thank you. So Bitcoin has a lot of scaling challenges. First of all, the cost over time is becoming exponentially more and more computationally difficult. Bitcoin is doubling its hash rate year by year, and with this hash rate exceeding computational costs over time, we have nothing to actually combat that cost. And development technologies such as layer 2s, there are not enough development technologies for Bitcoin that allow us to actually supplement for this cost. So as Bitcoin becomes increasingly more and more expensive over time, but the development frameworks are just not there, then what we worry is that Bitcoin will not have the mass adoption that we're looking for. And so Bitcoin adoption really is interdependent with the tooling that's involved. And so we lack modern tooling, and we do need to develop these tools. And another huge problem with Bitcoin and its scalability, and these are a little nuanced niche points, but they're very important to think broadly about, is that maximalism is not necessarily a favorable or even like a progressive style of innovating our technology stacks. And so when a Bitcoin maximalist is looking at you and looking at us, and we're trying to develop a framework that's actually going to scale Bitcoin, the problem that we're always facing is that when speaking with maximalists, the mentality alone is not anarchist enough in order to actually complete this narrative that they have about decentralization or sovereign data or even privacy for that concern, right? So maximalism is actually stopping innovation, and we need to open our minds a little bit more about what exactly our solutions could be for layer 2 or for Bitcoin. And the fact that we don't have enough trust as holders, most Bitcoin holders, if you're a holder of Bitcoin, I don't think most people would hold and trust others and other custodials with their account or even with private equity. So it's very hard to convince a central sequencer, especially a large capital fund, to stake a lot of tokens, especially in Bitcoin, when there's already so little of it. So how little of it? Well, first of all, we have many coins. We have WBTC, we have BTCB, we have CBBTC. But of all of this supply, we have about 219 million holders of Bitcoin, but realistically, there's only around 300,000 to 500,000 actually daily active users with and using Bitcoin. So most of the protocols that are out there are explaining how they have a yield optimized strategy for their layer 2 network. However, how is it that you can generate a yield when you don't have enough transactions? And the analysis that we've done does not prove that anybody who states that they have a yield optimized protocol in Bitcoin is lying. So you're lying. We know that you're lying. And we know that we're lying because there's only 250,000 Bitcoin in actual circulation. So the percentages don't match up. When you allocate the yield and the optimized yield, which is anywhere between 3 to 5%, and you split that across 90 different blockchain projects, there's not enough Bitcoin to go around to make that yield. So either somebody is faking the number or the money is not actually there. So how do you decentralize this liquidity? Because the problem with Bitcoin is that it's overly collateralized, but also overly centralized too. It's not even mentioning it. We go to the next slide. Yeah. So our challenges when trying to think of a Bitcoin layer 2. These are the challenges that you're going to have to think of. First of all, the building a cost-effective and fast ecosystem. Cost effectiveness of a layer 2 and the roll-up architecture is more of a data administration problem. If you have a DevOps that's actually engineering with you and your team, cost optimization is usually key when it comes to actually creating an infrastructure, or let alone a network. That's hard, but let alone you have to decentralize the sequencer. The decentralization of a sequencer is rough because you have to create a prover and a verifier relationship with computers. And they also have to enable a consensus that is strong enough to guarantee commitments to and from Bitcoin. So you have to enable some sort of sequencing relationship because BitVM2 and many of the other white papers that have come out about what exactly is a permissionless bridge in Bitcoin, it's always a centralized sequencer. There's never a decentralized sequencer in any of this. So when talking to a lot of Bitcoin maximalists, they're never saying, oh, like, thank God there's a centralized sequencer. They don't know about this. Like, Optimism is a centralized sequencer. Arweave is a centralized sequencer. They're all centralized sequencers. So, again, I'm gonna go through all of this, but eventually you have all of these project ending challenges, and so we needed to say, how are we gonna decentralize the sequencer? How are we gonna actually commit to and from Bitcoin using some sort of optimistic challenge process where we have a consensus? And how is it that we can actually bridge Bitcoin to an Ethereum node where we can actually lock in the GOAT BTC value, where we have a mint and burn with a verifiable proof of correctness somewhere? How can we do that? So ZKM. ZKM is a generalized architecture. I'm gonna explain a little bit more about what can we go to the next slide? Next slide, there we go. So ZKM. ZKM has benchmarks, but these benchmarks prove, these prove multiple things. First, ZKM is general enough for us to run Starks, Plonks, as well as Gross16 through multiple instruction sets to create a zero-knowledge proof. Zero-knowledge proofs usually are free. They're not actually computationally expensive, especially if you're using quick error arithmetic or you're using specialized ZK provers, for example, right? There's optimized ZKPs. In MIPS, you're using a generalized and constant size proof segment. And so these segments are in constant size, so it's easy for us to prove large amounts of data using programs such as in Go or in Rust, and we're gonna do this with data. We're gonna do this now with general data that we could not have done this otherwise with a token proof, such as others that are gonna require a token. Others, like Alio, require a token. Others that don't require a token are like MIPS architectures. So this is the decision there. We use a generalized framework so that we can create a zero-knowledge proof in the cloud that does not rely on a token, and it also gives us a general framework for how to create a consistent size of our execution traces so that Bitcoin and GOAT network can create a winter snitch signature that can be posted and verified to and from Bitcoin. And how? So our cost and the entire stack is realistically these segments. So first, to relay back to the first thing, you need a cost-efficient ZK rollup. What is that? Well, first you have to use an in-house ZK VM. So the ZK VM needed to be hand-selected. We chose ZK MIPS because it was general enough for us to create a generalized commitment and verifier. The other thing is that we needed to generate a low-cost zero-knowledge proof. So because the cost of ZK MIPS is generally pretty conservative, the speed outweighed the cost. And so we have a well-balanced node that runs now roughly in terms of Amazon cloud credits. You can expect it to be anywhere around 8,000 to 9,000 monthly, but depending on DA and depending on prover and depending on how you're setting up your system, the key is that you can optimize memory. You can also optimize performance of a ZKM. So I'm giving you general cost, but I'm saying that the cost is already conservative. You can continue to optimize further. So you data sync with this ZKM. We have a roll-up economic model. We have an interesting white paper as well as a beige paper on our website on goat.network. I would give you a full synopsis of what that is, but it's essentially an economic paper on how exactly GOAT Network intends to create a yield optimized layer 2. So what that means is that Bitcoin is our layer 1, and we are generating a verifier script through Bitcoin VM2, right? Or BitVM2. Our consensus relies on a decentralized sequencer that uses ZKM to roll up block space in order to create a commitment and to verify that commitment through Taproot. And so Taproot, acting as our verifier, we're able to then say some block space had some proof allocated to MEM, and we can verify this directly on Bitcoin. So the last panel was talking a lot about how now we do have a actual native solution for Bitcoin. Is this built yet? No. This is phases. So I want to point out that this is green, it's yellow, and then it's purple. So this is our phases. So it's effectively what we have done now. Today we have created the ZKVM, we have decentralized the sequencer to a layer 2, and we are also optimizing the token allocation of yield. So yield that's generated on Bitcoin can now optimize yield on a sequencer. And I'll show you what that means. So that's the realistic path forward. Can we go to the next slide? Thank you. This is effectively the diagram of what Goat Network is going to do. At the end of the day, you have BTC holders that can lock directly on Bitcoin layer 1, and you can decentralize the sequencer. Decentralized sequencers own the total lock of the Bitcoin, but they have a multi-party computation and an agreement of who actually makes the commitments to and from Bitcoin. Right? So you create the SSR or the SRS ahead of time, and then now you have a strong guarantee that the committee of these operators, the one that's making the commitment, has the existential honesty assumption with Bitcoin. That is the risk. The risk of the commitment being incorrect is the fact that the one making the commitment can change the data when it's being committed. But when you have a multi-party computation, you're actually enabling the system to have an optimistic challenge with saved data without necessarily revealing it. We're going to then issue YBTC. So every token on the network is gas, right? Gas tokens are Bitcoin. So everything from the ground up, we can relock this into a sequencer and then generate YBTC, which is the yield of the protocol. So when sequencers earn rewards, they're effectively minting the yield of the protocol because people have already staked and locked the token of gas, which is Bitcoin, to the sequencer. Okay, so you can do this from either L1 or L2. I hope that's clear, and we'll go to the next slide. Cool. I like to give this image of what exactly the end game is. Why are we doing all this? At the end of the day, we're creating an entangled rollup. It's a lot, but it is true. We have an entangled rollup scheme, and in the middle we have Bitcoin, and onto the side we're using BitVM2 and Taproot. We also want to be able to enable operators that have a multi-party computation in which this committee commits and verifies through Bitcoin. We then have operators that run an optimistic challenge process, and then we use such as Starks, Plonks, and Gross16 to create validity proofs in order to create an effective rollup in ZKM. And now the Ethereum virtual machine is the execution environment of Go. And so we're using Geth, and so this way we can actually wrap the node in Geth with MIPS. So it means that we're able to perform what's known as strong interoperability. Strong interoperability is when we can prove the state of execution as well as the node itself, as well as the time of block, how many blocks, and data that is on the chain now versus what it was yesterday. So effectively means we can prove time, block time in real time, and also make execution traces, which are effectively, I create a state of a program, I'm able to then prove the state of that program afterwards. So it means that we can say chain A had performed some transaction of either stake, lock, or deposit, and chain B is willing to accept the arguments passed to chain A because both chain A and chain B agree to the same prover and verifier, which is the decentralized sequencer. The decentralized sequencer holds the same zero-knowledge proof. Therefore, both chain A and chain B can rely on this idea of consensus between one another. Now, the ZKM is a little bit of a mysterious protocol, but I want to show you how general it is. Pavel over here actually has a whole other side of the demonstration lined up for you of how ZKM works and an example of it running in real time. And in case you wanted to use ZKM in your own Bitcoin project or even using it on Go, I would suggest, yeah, this is going to be pretty interesting. So take it away. Thank you. Hello? Oh, yeah.
Of course. Awesome. All right. Hey, everyone. My name is Pavel, and I'll be going over a real-world example using ZKM. A scenario that is currently present is that there are data brokers. Data brokers exist to essentially take data that is present in public domains, public records, or they go out and they buy it directly from providers, and they do so for advertisement purposes or different types of analytical purposes. And there are self-reporting mechanisms as well. So for example, survey data is collected from different users, and that survey data is also used within these systems. There currently is no way to collect this data in a way where it doesn't depend on a single centralized provider. We want to create a way where data is, anybody can actually send the data, and that data can be validated directly on the user's computer, and as a result, that data can be then appended to a database with the correct data types associated with it. So I don't need to essentially run any type of front end or back end. I can just have the database where it can accept a proof as well as the data, and you can be guaranteed that even if anybody, an untrusted source comes in, as long as they have a proof, a validity proof of that data validation, they can submit it. So I guess next slide. And next slide. Can we click on? Oh. Yeah. So we want to collect data from the user directly, and we want to reward the correct information with the proof of correct execution. And users can redeem the proof for an on-chain reward. In this case, I would demonstrate the reward being an NFT. Next slide. So this is the overall architecture of how it looks like, very simplified. User provides input. It goes into the ZKVM program. It then outputs a proof. And using those same inputs paired with that proof, the user can insert the data into the database in a way that you don't have to perform any additional data validation checks because the ZKVM already operates in that way. Next slide. This is a bit more complicated diagram. It basically outlines what is going on internally. We take the inputs and we structure them, put them into the guest program. The guest program is the actual program that runs within the ZKVM. And then that goes into and that outputs a proof, and then that proof gets returned to the user, and then, same as the previous diagram, we get the proof and the inputs directly going into the database. Next slide. The whole step-by-step process, program execution, proof generation, and then proof verification is the final step. Next slide. And the main benefits of this is we can upload any information directly to the database without a centralized backend checking that data. So essentially, we can do a super scalable way, and a way that guarantees that the data is, in fact, passes validation checks. And then one use case is that the form data validation for community compiled data sets. We see that AI and all these models are being trained on the different data repositories. So we can actually create a community collected data repository from anyone, and no single centralized provider can come in and change that data because it's secured via these ZK proofs. Next slide. And we have compliant data brokerage services and checking to see if the person has valid data before sharing. Next slide. So over here, I have a brief demo of this, and I guess we'll switch to the overall workshop slide. Perfect. So over here, I have a speedrun Ethereum app, and let's see. I'm gonna exit full screen just a moment. Okay, perfect. So I have over here, I can provide an email, an ETH address, and a number. When I click submit, this will go in and generate a proof related to the submission. So if I put in some basic information about the data and validity, and I click submit, this routes to an API, and this API makes a request and generates a proof of execution. So over here, we have this being run within the ZKVM, and I know that's very small within this, but essentially we are coming in and we are running this program inside the ZKVM. We are given the execution and the results of that execution. Now, this took 30 seconds. This is essentially running a version where it's executing only. If I were to do a true execution, so if I were to make the exact same request, I might have to restart the back end, click submit, and then as a result, we can go in and we can see that there is a seg number in here. This is however many segments that it takes to prove this. And each segment, the amount of time that it'll take to prove, so here's a previous proof. So there's 31 segments, and it took roughly 210 seconds, or 1,210 seconds in order to prove and generate the prover output, or the proof of that computation. And the exact program for this proof of computation is within here. It's a Golang-based program. And all we're doing is we're checking and we're validating the email, the ETH address, and the number. And this is passing through this checker, which checks each and every one. And this is running within the ZKVM. And so it takes roughly 1,200 seconds, which is roughly 20 minutes in order to generate the proof. Well, we don't have that much time. So I did create a pre-created proof where once the proof is generated, we get the output. We can then send it as a client, and we send the transaction with the proof. Then we can see that we have the hash. I am the owner, I am the one who sent it, and I have an NFT of the resulting data. So I've essentially sent data. I have generated a proof with the input data, and then after that, I essentially relayed that information and proven that this proof, as well as the inputs associated with the proof, are correct and valid. And this is checked directly on the blockchain, and as a result, we can guarantee that the execution did in fact happen, and then this is a correct output and result. Now, you know, there's additional validation checks. If I try to mint the same NFT with the same data, it'll say, no, you can't do that because there's a duplicate submission. So this is how we prevent people from reusing the same proof or reusing the same information to the same data set. So we can include additional validation checks directly onto the smart contract because it knows what data that you're actually inputting. So as a result, we can have a append-only database where if you generate a valid ZK proof, you can append certain data to the information and then receive reward, in this case, an NFT where you can then transfer it and do what information from that. The code is open source, so you can try this out yourself. I've included the repo. And yeah, thank you. That's all I have to present. Yes.
So what's the advantage if you anyhow send the data to the database? So what is the advantage of the proof compared to the simple SHA hash? Right, so anyhow the privacy is compromised against the database because we send the input. So why shouldn't we just use a hash for that?
So, well, the hash doesn't necessarily expose the data. It just shows that the data that was provided matches that hash that was sent. So I can't, from this hash, I can't really derive the data of the information that I'm inputting. So in this case, I don't know what data that I'm committing. I just know that it's this data.
So you just send the proof of the input, you don't send the inputs?
No, you can send the inputs. And this can be to a centralized database as well. So the data broker and provider can also, you know, say, well, you know, like we will only accept information that you send to us directly. And so as a result, the data broker can have certain types of restrictions based on that. Or this can be like an open IPFS-based system where you can directly commit to an open data structure for this. So it's more of like a primitive where you can take this and bind this to different implementations based on the use case. If you're a data broker, you might want to be, private with the data, but you still want anybody to be able to commit if they have like certain, if they pass certain validation criteria. Now, of course, we're doing it with very simple, email form, and this itself takes like 20 minutes. But the idea is that we can take arrays or we can take entire spreadsheets and then compile it down into different individual records and then have all those records be validated without requiring a centralized database, without requiring a centralized backend or front end to be able to manage this. So I can run this all locally on the device, and then afterwards I can just append to the database directly. I guess there's one more slide over here as well, just to what the limitations are, of course. So, one of the things is that we can't check if the data exists before the payment is being sent. So, that's unless I append directly to the database, unless I append directly to the blockchain, then there's no way to really check if the data is available. So you likely need to have this matched with like a different provider with like, for example, BNB has a Greenfield, which is basically like a data storage layer. So likely some combination of architecture would be used in order to support this specific use case. But the idea is still the same. We can append to the database with a valid proof without requiring so much infrastructure in terms of back end and front end. Just with the ZK proof, you run it through the checker, and then you can send the data. Perfect. I think that's.
Clears up the like what you are can and cannot do. That's what these other examples are for as well. Like how would you complete a full program in use without rollup? Is that you're creating a program that you want to be able to verify data, or it's public data, and you can verify it against something. Yeah, he created a proof, but then the guy that's submitting the input can also verify whether or not the data had ever even been included to begin with. So now you can verify, not like accounts, doesn't mean it's, ZK is not like a Ethereum thing, right? Like, but you can set permissions on like input and output variants on a ZKM. So you can upload it through BNB Greenfield, and why that's a good idea is because it's a smart contract DA layer on Binance. And then you have Bash, which is the way of doing anything in your terminal, so you can actually create multiple environments to spread out your proof, so you can have multiple instruction sets running parallel. So the ZKM is, it's just a machine that's running, and of course you can set up proxies so you can protect. You don't want to do injection attacks with a DB. Even with Alio and other ones, any prover network that allows you to just inject straight into the database means that you can read from it and you can do a lot of bad things. You don't want to inject in DDoS. So that's why you would run those kinds of things. So just think about your stack and then like layer those on top of it. I think we're out of time though, yeah.
Yeah.
But
You
thanks.
guys are doing a great job. That's fine. Yeah.
Awesome.
Okay. Thank you so much, Pavel and
Thank you.
Dylan. Appreciate you.